Hello and welcome back to Matt's Math Tutorials. Potentially for the final time. This will probably be my last video. It's always possible that I get forced into making more, but the plan is for this to be the last one. So if you've watched any of my videos, thank you. So today we're going to be covering integration by parts, which is a very useful technique for doing integrals. And it starts off basically with a formula. I'm not going to derive the formula because I don't know how and I don't really care. But this is integration, okay, by parts. So the formula is the integral of u dv equals uv minus the integral of v, okay, v d. I'm gonna have to be very careful about making sure my v's are angled enough in this video. But anyway, so this is the formula. Now, I think the best way to show how to do this is to just do examples. So I'm going to do three example problems. So the first one will be the integral, that was much better, of x e to the x dx. Okay, so basically what we need is we're going to need a u, oh, I'll write this over here. We're going to need a u, we're going to need a v, we're going to need d, u, and we're going to need a dv. So within this, the thing that we're given, we're going to have u and we're going to have dv, and then we just have to work backwards to find du and then v. So basically, we're going to choose something for u that we can differentiate and choose something for dv that we can integrate. So for this, there's a lot of different options. You can do x and e to the x dx. You can do ex and then these two together. You can act like there's a 1 here and do that and then these, or you can do you can do these two together and just the dx. I would say kind of just ignore the dx. For the most part, it's going to just be attached to the one you're integrating. It can kind of get complicated. There's a practice problem where you just do the dx by itself for one of them, but I don't know, it's weird. So uh, we need u to be something we can differentiate. So we can differentiate both of these pretty easily. So we need some dv to be something we can integrate, but we can also integrate both these pretty easily. So there are rules for, well, not rules, but more guidelines for which one to choose. So to quote the book, try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Then u will be the remaining factors of the integrand. And then 2, try letting u be the portion of the integrand whose derivative is a function simpler than u. Then dv will be the remaining factors of the original. So if we look at the first guideline, let dv be the most complicated part that fits a basic integration rule. So these both fit a basic integration rule, but this is clearly the more complicated part. So based on the first guideline, we would have the ex be dv. Now, the second guideline says that you should let u be the portion whose derivative is function simpler than itself. So if we differentiate the x, we're just going to get 1. Now, if we differentiate the ex, we're just going to get ex again. So it's not going to make it simpler. So by this guideline, we should make u be x. So basically, both guidelines are telling us that u is going to be x, and dv is going to be e to the x, technically dx as well. It's this whole part. But like I said, the dx kind of just, gets dragged along with it usually. So now, if we differentiate, this means that du is basically just 1, or if you want to look at it as being dx, because you're differentiating in terms of u, you're doing x, so this becomes basically dx du. Because of course, if this was x and you're differentiating in terms of x, it would just be 1, but we're differentiating in terms of u, so it becomes dx. Now v, if you integrate this, you would put this whole thing in an integral like this, and this is where the dx kind of just gets dragged along. And now, of course, this is just going to be e to the x, right? Because that's how it works. And there's going to be a plus c, but we can do it at the end. So for now, we just ignore it. So Now we just try to fit all these into the formula. So if we look back at this, I'm going to rewrite it. So uv minus, I forget this formula a lot, I'm not going to lie, v du. So notice that we don't need, actually we need everything. Well, we don't need dv. So the original thing is not going to be in the formula, but that doesn't really matter because dv is the same as v is this. Anyway, so u is x, v is ex, and then minus integral v is ex, and du is dx. So this. Now, of course, we can simplify this. This will stay the same. That probably won't be simplified, but this is of course, e to the x, right? We already did that. We integrate e to the x, and then now we do the plus c. So basically, this is our final answer. So the integral of x ex dx equals x e to the x minus e to the x plus c. And yeah, so now you could probably do some like factoring out if you wanted to, but that's the general idea. So now we're going to do another problem. That was probably like, one of the simpler ways you could use it. So now we're going to try to find the integral of x squared and then natural log of x dx. So now we're going to set up our thing again. We're going to need a u, we're going to need a du, we're going to need a v, we're going to need dv. And of course, these two we're going to get from the formula itself. And then let me rewrite the equation. So uv minus integral, was it v du? Yeah. Okay, so we need d to be something, or we need u to be something that we can differentiate. So we can differentiate that. Can we differentiate the natural log of x? I think we can, right? I know it's, um, this goes to 1 over x. I believe this is differentiating. Integrating this, I think is not as easy, if I remember correctly. So we could differentiate either of them, but let's see. Can we integrate? Which one can we integrate? Well, let's see. Yes, the natural log of x is harder to integrate. So we're going to have u be the natural log of x. Let me just make sure. Yeah, this is what the textbook wants. And we're going to have dv be x to the second power. Now, it did say that you should try to make um, u be something that will get simpler, and this definitely does fit that. This will get simpler, but again, that other guideline says you kind of want dv to be a more complicated part. Um, and of course, you can't really integrate this as easily, so it kind of forces you into this. So that means that du is 1 over x, and of course the dx kind of gets lobbed on there. Oh, same thing here, I believe. Yeah. And then this is, of course, if you do the power rule kind of backwards, you get x to the third over 3, right? When you do the derivative of this, that 3 is going to drop to be a coefficient, and then they'll cancel out. So it'll be that, and then, yeah, so no dx on there. Okay, so now we plug into our formula again. So the u is natural log of x, v is x to the third over 3, so I'm going to put that right here just to make it look better, minus integral, what's v? Natural log of x, and then divided by x, oh wow, divided by x, actually, I'm just going to do times 1 over x dx. All right, so now can we simplify this any further? Oh, I made a mistake. V is not the natural log of x. V is x to the third over 3. And that makes more sense in terms of that. Okay, so now of course we can simplify this further. Let me just make sure. Yeah, this part is correct. And that won't be simplified because it doesn't really look like something you can simplify. But anyways, you get x to the third, natural log of x divided by 3 minus, this will just end up being, that'll cancel out with that, so that'll just be x squared over 3 dx. And then of course that turns into, right, you can do the minus 1/3 of this. And then we already did that. That's of course x over 3, or x to the third over 3. So then we have x to the third natural log of x over 3 minus x to the third over 3 times 3 is 9. And then, of course, you add in the plus c. And this is our final answer for the integral of x squared natural log of x. All right, so again, pretty simple. Once you have these four things, plugging it in is pretty easy. But now we're going to look at another example where we're going to have to do this multiple times. Because you can imagine if you get something in this part of the formula that is not very easy to integrate and you have to do integration by parts again, you can kind of just like get into, one of those like Russian nesting dolls where you just do integration by parts, but that gives you something plus integration by parts, and then that gives you something plus integration by parts. So we're going to look at a method of doing it a lot of times all in a row. So this is called the tabular method. I think my writing gets bigger as it goes. I don't know. Yeah, it starts smaller, it gets gradually bigger. It's whatever though. All right, so this is the tabular method. So again, this is for when you are going to have to do it a lot of times in a row. So this, let's do this. X squared sine 4x dx. All right, so like usual, u, v, du, dv, uv minus derivative v du, not derivative, integral. Okay, so let's see, what should we do? Well, we need a u and we need a dv. Now, again, it kind of looks like we could differentiate this, we could differentiate this. We could also integrate this. Can we integrate this? Probably, right? If we really put our mind to it. Um, let's see. So we are going to, book says we're going to have this be x squared and this be sine 4x dx. All right, let's see. Does it say why we want to do that? Not exactly. I think it's because, oh, right. Um, so when you have a trigonometry thing like sine, if you do the derivative or the antiderivative, right, derivative or equal, it's going to just kind of flip-flop between being sine, cosine, sine, cosine, sine, cosine, and it's going to kind of give you a repeating loop, which is kind of why we do this tabular method. And that'll also be like a different thing later on where you have to like combine like anyways, it kind of just gives you a repeating loop. So we want to have the one that we're differentiating be the x squared part, because if you do that enough times, you'll just get to 0, and then you can kind of disregard everything after that. So that's why we're doing this. Now that means du is, well, actually, like I said, we need to do this a lot of times, so I'm actually not going to do this. For now, let's just have the u and dv. So now basically you make a chart. And this is going to have 3 rows. Nope, 3 columns. However many rows we need. So this is going to be u, u prime, u double prime, oh, double prime, u triple prime, etc. So basically we're going to be having u and its derivatives. Actually, I'm just going to write that, because that's how the book writes it. U and its derivatives. All right, and then this will be dv and its antiderivatives. And then this will be alternating signs. So basically, let me give myself some more rows here. So we're going to start with putting u right here. Of course, u is x squared. And we're going to put dv right here. We know dv is sine 4x. All right, and we're going to have alternating signs, which just means plus, minus, plus, minus. All right, so now down this column, we're just going to do the derivative of this a bunch of times. So first derivative 2x, and then 2, and 0, right? So we're doing the derivative of the box above it. So now same thing here, but with the antiderivatives. So the antiderivative of this, I'm not going to go through how to do this, but I'm just going to copy what the book has. You could kind of work backwards, knowing that this is going to become a coefficient on the outside, and of course it has to cancel out. And of course it's going to flip signs. as well. And then this is negative 1/16 sine 4x, and this is 1 over 64 cosine 4. So you can see that this could go on forever. This column right here, you could just keep going down and down, and it's gonna, flip the sign every other time, and the power of 2 right here is just gonna keep increasing. Actually, I think it's going powers of 4. Yeah, it's going powers of 4. So you can see that part will go on forever. So that's why we want this part to be the derivative, because this will stop. If we did this and its antiderivatives forever, it would also go on forever, and that would not help us. So now what you do is this actually tells you the terms. So what you do is you're going to go, let me do like red. You're going to go across and then diagonal, across, diagonal, across, diagonal, and then across diagonal. But we don't need this term because this is 0. So we can stop right here, basically. So now, what do I mean by that? Well, these tell us the terms. So if we have, remember the original thing was x squared sine 4x dx. So now we can say this equals, the first term will be this times this times this times this. Actually, let me do that thing that the Khan Academy guy does, because it's kind of cool. So this times this times this. So the sign's going to be negative. It's going to be 1/4 x squared and then cosine 4x. And that's the entire first term. And then it's going to be this times this times this. So the sign is going to be negative times negative, so it's going to be positive. And then it's going to be 2 times 1 over 16, so 1 over 8. And then x sine 4x. All right. And then the next term, of course, is going to be, let's see, what should I do? Magenta, sure. This times this times this. So that will be positive, positive, so that'll be plus, and this is, of course, going over right here, if that wasn't clear. That would be 2 over 64, so that would be 1 over 32. No x, just cosine 4x. And then you can see why this would not matter, right? Because we would do this times this times this, and it would just be 0 times whatever for infinity. So it does not matter. So this is our final answer. Now you could do this. Oh, wow. There's nothing specific about this problem as opposed to the 2 previous problems we did that makes tabular method work. It's just that, oh, plus C. It's just that it's like slower if you're just doing it one time, but for this we would have had to do it a lot of times because we would have gotten, of course, this thing would have just made it flip back and forth, and this would have taken obviously 3 derivatives to get to 0. So when we did this part, we would have got another thing that we had to use integration by parts. So if you're going to have to do it multiple times, this method is pretty good. And usually you can tell because it's going to have like trigonometry and then something like this where it's going to, eventually differentiate down to 0. All right, so this has been integration by parts. Like I said, this should be my last video. So thank you guys for supporting me, all, like one viewer that I have. But yeah, hopefully I don't have to do this again. And if I do, that sucks. But goodbye.